The cosmos is a grand theater of stellar evolution, where stars are born, live, and eventually, die. For stars roughly the size of our Sun, or up to about 8 times its mass, the dramatic conclusion of their lives doesn't involve a cataclysmic supernova. Instead, they gently, yet profoundly, transform into white dwarfs, enigmatic celestial objects often referred to as stellar corpses. These aren't just inert remnants, they are incredibly dense, compact, and profoundly fascinating laboratories of physics, holding secrets that continue to challenge and expand our understanding of matter under extreme conditions. The journey to becoming a white dwarf is a long and intricate one. A star like our Sun spends the vast majority of its life, billions of years, in a stable phase, fusing hydrogen into helium in its core. This process generates outward pressure that perfectly counteracts the inward pull of gravity, maintaining a delicate equilibrium. However, eventually, the hydrogen fuel in the core begins to deplete. As this happens, the core contracts and heats up, causing the outer layers of the star to expand dramatically, transforming it into a red giant. This expansion is immense. If our Sun were to become a red giant, its outer layers would engulf Mercury, Venus, and possibly even Earth. Once the red giant phase commences, the star begins to fuse helium into carbon and oxygen in its core, and hydrogen fusion continues in a shell around the core. This is a temporary reprieve. Eventually, the helium fuel also runs out, and the star isn't massive enough to ignite the fusion of heavier elements like carbon and oxygen. At this point, the star can no longer generate enough outward pressure to support itself against gravity. The outer layers, now unbound, are gently expelled into space, forming a beautiful and often spectacular planetary nebula. This isn't related to planets. The term arose because early telescopes made these glowing shells of gas look like planetary disks. What's left behind is the star's hot, dense core, the nascent white dwarf. This core, despite containing a substantial fraction of the star's original mass, typically 0.5 to 1.4 times the mass of the Sun, has shrunk to an incredibly small size, comparable to that of Earth. This remarkable compression leads to astonishing densities. A single teaspoon of white dwarf material would weigh several tons on Earth. Imagine fitting an entire star's worth of mass into a sphere only a few thousand kilometers across. It's this extreme density that gives white dwarfs their peculiar properties and makes them so scientifically valuable. The key to understanding how a white dwarf resists gravitational collapse lies in a quantum mechanical phenomenon known as electron degeneracy pressure. Unlike normal matter, where atoms are mostly empty space and can be squeezed closer together, the electrons within a white dwarf are packed so tightly that they obey the Pauli exclusion principle. This principle states that no two electrons can occupy the same quantum state simultaneously. When electrons are forced into such close proximity, they generate a powerful outward pressure, independent of temperature, which is sufficient to counteract gravity and prevent further collapse. This is why white dwarfs are often described as being supported by the stuff of quantum mechanics. This degeneracy pressure is incredibly robust, but it has limits. If a stellar remnant exceeds a certain mass, known as the Chandrasekhar limit, approximately 1.4 solar masses, electron degeneracy pressure alone is insufficient to prevent further collapse. In such cases, the star's fate is far more dramatic, leading to either a neutron star or a black hole. But for white dwarfs, this quantum pressure provides a stable, though slowly evolving, final state. When a white dwarf first forms, it's incredibly hot, radiating away residual thermal energy from its stellar past. However, without any ongoing nuclear fusion, a white dwarf slowly, inexorably, cools down over billions and even trillions of years. It gradually fades from a brilliant white to a dim red, and eventually, if the universe lasts long enough, it is theorized to become a completely cold, dark black dwarf. This latter stage is purely hypothetical at present, as the universe simply hasn't existed long enough for any white dwarf to cool down entirely. So, the coolest white dwarfs we observe today are still radiating some residual heat. White dwarfs are not merely cosmic relics, they play a crucial role in our understanding of the universe. They serve as standard candles in astronomy, objects with a known intrinsic brightness, which allows astronomers to measure vast cosmic distances. This is particularly true for type Ia supernovae, which occur when a white dwarf in a binary system accretes matter from a companion star, eventually exceeding the Chandrasekhar limit and undergoing a catastrophic thermonuclear explosion. These supernovae are so luminous and their brightness so predictable that they are used to determine the expansion rate of the universe and even to infer the existence of dark energy. Furthermore, white dwarfs are excellent laboratories for studying extreme physics. Their intense gravitational fields can cause light to be gravitationally redshifted, a phenomenon predicted by Einstein's theory of general relativity. The study of their atmospheres allows astronomers to probe the elemental composition of stellar cores that were once active. They can also host planetary systems, with recent discoveries showing debris disks around some white dwarfs, suggesting that planets or their shattered remnants can survive the red giant phase and orbit these dense stars. Some even show evidence of polluted atmospheres, where heavier elements from devoured exoplanets or asteroids have settled, offering a unique window into the composition of planetary systems beyond our own. The ongoing cooling of white dwarfs also provides a cosmic clock, helping scientists to estimate the ages of star clusters and even the age of the galactic disk. Yet, despite their apparent stability, white dwarfs are far from inert. Their extreme conditions can lead to spectacular cosmic events, particularly when they exist in binary systems, pairs of stars orbiting each other. If a white dwarf has a close companion star, its immense gravity can start to pull matter, primarily hydrogen, from the companion's outer layers. This stolen material spirals down onto the white dwarf's incredibly hot, dense surface, forming an ever-growing layer. As more and more hydrogen accumulates, the pressure and temperature at the bottom of this layer increase dramatically, eventually reaching a critical point where it triggers a runaway thermonuclear fusion reaction. This sudden ignition causes a brilliant, temporary brightening of the white dwarf, known as a nova. Unlike a supernova, which often destroys the star, a nova is a surface event. The white dwarf itself survives, shedding the fused material back into space, only to potentially repeat the process again and again over thousands or millions of years. These recurrent novae are powerful cosmic beacons, showcasing the dynamic interplay of gravity and nuclear fusion on a stellar corpse. Even more dramatically, if a white dwarf continuously accretes enough material from its companion to push its mass over the Chandrasekhar limit, that critical 1.4 solar masses, electron degeneracy pressure can no longer hold. The star undergoes a catastrophic, complete collapse, igniting its entire carbon-oxygen core in an uncontrollable thermonuclear runaway. This is a type Ia supernova, one of the most powerful explosions in the universe, briefly outshining entire galaxies. These standard candles are crucial tools for astronomers, allowing them to measure vast cosmic distances and, most remarkably, to discover that the universe's expansion is accelerating, hinting at the mysterious force known as dark energy. The study of white dwarfs continues to push the boundaries of astrophysics. Beyond their roles in novae and supernovae, they offer unique insights into the properties of matter at extreme densities, providing laboratories for testing theories of quantum mechanics and general relativity. Scientists are also exploring whether white dwarfs could host life. While the stars themselves are inhospitable, their long cooling times mean that any planets surviving their parent star's red giant phase could potentially remain warm enough for liquid water for billions of years, powered by the white dwarf's residual heat. The discovery of polluted white dwarfs, those with atmospheres contaminated by heavier elements, provides direct evidence that these stellar remnants can consume planetary material, offering clues about the composition of exoplanetary systems and how they evolve over cosmic timescales. Ultimately, white dwarfs are a testament to the diverse and often surprising ways in which stars end their lives. They are not merely faint embers of former glory but active participants in the cosmic ballet, continuously revealing new secrets about the universe's past, present, and even its distant future. Their quiet, cooling journey through the eons will, one day, culminate in the hypothetical black dwarf, a truly cold, dark, and utterly invisible stellar remnant, a cosmic tombstone awaiting the very end of time itself. So, while they may seem like the universe's ultimate quiet observers, white dwarfs are anything but static. Their extreme densities and powerful gravitational fields make them engines for some of the most violent and energetic events in the cosmos. Imagine a star the size of the Earth, yet weighing as much as our Sun. That's the kind of mind-boggling compression we're talking about. This density isn't just a curiosity, it's what dictates their very nature and their interactions with their surroundings. The study of white dwarfs isn't just about understanding stellar remnants, it's about pushing the boundaries of physics itself. They are cosmic laboratories where we can observe phenomena that are impossible to replicate on Earth. For instance, the gravitational redshift of light from a white dwarf provides direct observational evidence for Einstein's theory of general relativity. Light literally loses energy as it climbs out of the white dwarf's immense gravity well, shifting to redder wavelengths. This isn't just an abstract concept, it's a measurable effect that confirms our understanding of spacetime. Furthermore, the atmospheres of white dwarfs are like time capsules, preserving the chemical signatures of their former lives. By analyzing the elements present in their outer layers, astronomers can deduce the composition of the star's core that once fueled nuclear fusion. And sometimes, these atmospheres reveal something truly unexpected, the presence of heavy elements like iron, magnesium, and silicon that shouldn't be there. This pollution is compelling evidence that white dwarfs are actively consuming the remnants of their own planetary systems. It means that after the parent star swelled into a red giant and then shed its outer layers, any surviving planets or asteroids might have been gravitationally disrupted, fragmented, and then slowly spiraled into the white dwarf, leaving their chemical fingerprints on its surface. This gives us an unprecedented look into the final fate of exoplanetary systems, offering clues about how common rocky planets are and what their ultimate end might be. The saga of a white dwarf is one of quiet determination, a long, slow fade into cosmic obscurity. Yet, within this fading, there's incredible activity and revelation. They stand as enduring monuments to stellar lives, silently orbiting through the galaxy, each one a unique record of a star's fiery youth and its eventual, compressed serenity. And as our observational capabilities grow, we continue to peel back the layers of these stellar corpses, finding that the universe's most dramatic stories often unfold in its most unexpected places. And what of the future of these cosmic remnants? While the universe hasn't yet existed long enough for any white dwarf to cool completely into a theoretical black dwarf, a state of absolute cold and darkness, a true stellar ghost, their slow, inexorable journey towards this ultimate chill continues. This gradual cooling makes white dwarfs incredibly valuable as cosmic chronometers. By precisely measuring their temperature and luminosity, astronomers can estimate the age of the star clusters they reside in, offering crucial insights into the formation and evolution of galaxies, including our own Milky Way. It's like finding a cosmic stopwatch, meticulously ticking away the eons. The sheer longevity of white dwarfs also raises fascinating questions about the very distant future of the universe. In the far-off epochs, long after all the brighter, more massive stars have faded, these dimming embers might be among the last visible objects in a vast, dark cosmos. They could potentially serve as the ultimate cosmic graveyards, silently bearing witness to the universe's ultimate fate. Imagine a universe so old that all the hydrogen fuel for new stars has been exhausted, and even the red dwarfs, the smallest and longest-lived stars, have finally winked out. All that would be left are these cooling white dwarfs, neutron stars, and black holes, adrift in an ever-expanding, increasingly empty void. The intricate dance of a white dwarf in a binary system presents another layer of complexity and wonder. While we've discussed novae and type Ia supernovae, these systems also offer a unique opportunity to study gravitational waves. As two compact objects, like a white dwarf and a companion star, orbit each other, they ripple spacetime, sending out gravitational waves that future observatories might be able to detect with greater sensitivity. This could open an entirely new window into understanding these dense objects and the extreme environments they inhabit. Furthermore, the pollution of white dwarf atmospheres by devoured planetary material provides a unique archaeological record of exoplanetary systems. It's like sifting through the cosmic ashes to find the remnants of long-dead worlds. By analyzing the precise chemical fingerprints left on the white dwarf surface, whether it's the signature of rocky planets rich in silicon and iron, or water-rich bodies hinting at ancient oceans, scientists can reconstruct the composition of the planetary bodies that once orbited these stars. This offers invaluable data for understanding the diversity of planetary compositions across the galaxy, and perhaps, even the prevalence of water-bearing worlds beyond our solar system. In essence, the white dwarf, often perceived as a mere end state, is a vibrant and dynamic cosmic entity that continues to surprise and inform us. From acting as precise cosmic clocks and standard candles to revealing the destructive dance of stellar binaries and providing forensic evidence of vanished planets, these stellar corpses are anything but dead. They are profound reminders that even in death, stars leave behind a legacy that continues to shape and illuminate our understanding of the vast, intricate tapestry of the universe. Their quiet existence is a testament to the enduring power of physics and the endless secrets held within the cosmos, waiting to be unveiled. As our technology advances, our ability to probe the secrets of white dwarfs only grows. New generations of telescopes, both ground-based and spaceborne, are constantly refining our understanding of these stellar remnants. Future missions like the Nancy Grace Roman Space Telescope and the Square Kilometre Array, SKA, promise to unlock even more mysteries, from precisely measuring the distances to type Ia supernovae, further refining our understanding of dark energy, to detecting the faint whispers of gravitational waves emanating from binary white dwarf systems. The precise measurements of white dwarf temperatures and luminosities, refined by these advanced instruments, will allow us to chart their cooling curves with unprecedented accuracy. This, in turn, will give us an even more precise cosmic clock, potentially allowing us to date the oldest star populations in our galaxy with remarkable precision and contributing to a clearer picture of the Milky Way's early formation. Perhaps the most enigmatic aspect of the white dwarf saga is their hypothesized ultimate fate, the black dwarf. While no black dwarfs have ever been observed, because the universe simply isn't old enough for any white dwarf to have cooled down completely, they represent the theoretical endpoint of stellar evolution for sun-like stars. A black dwarf would be a truly cold, dark, and utterly invisible stellar corpse, a dense sphere of degenerate matter, radiating virtually no heat or light. Its existence would be a testament to the immense timescales involved in cosmic processes, a silent monument to a star that lived for billions upon billions of years before finally succumbing to the cold embrace of the universe. The very concept of a black dwarf pushes the limits of our imagination, forcing us to contemplate a universe far older and colder than anything we can currently observe. They are the ultimate cosmic tombstones, representing a universe where all the stellar fires have finally been extinguished, leaving behind only the cold ashes of what once was. Ultimately, white dwarfs are far more than just dead stars. They are crucial laboratories for understanding matter under extreme conditions, testing the very limits of quantum mechanics and general relativity. They are cosmic time capsules, preserving the chemical fingerprints of long-gone planetary systems and offering insights into the formation and evolution of exoplanets. They are stellar workhorses, providing the precision necessary for measuring the expansion of the universe and unraveling the mysteries of dark energy. From their fiery birth as main sequence stars to their dramatic transformation into red giants, and finally, their serene, long cooling as white dwarfs, these celestial objects embody the grand, ongoing cycle of the cosmos. Each white dwarf, quietly drifting through the vastness of space, holds within its incredibly dense core the accumulated history of a star and the potential to unlock deeper secrets about the universe itself. Even with all we've learned, the story of white dwarfs is far from complete. There are still many active areas of research that promise to reveal even more profound insights. One such area involves the study of magnetic white dwarfs, which possess incredibly strong magnetic fields, sometimes billions of times stronger than Earth's. These powerful fields can significantly influence how matter accretes onto the white dwarf, affecting the dynamics of binary systems and even altering the properties of their atmospheres. Understanding their origin and evolution is a key puzzle in stellar astrophysics. Perhaps one of the most exciting frontiers is the continued search for exoplanets orbiting white dwarfs. While the violent red giant phase would seem to sterilize any planetary system, evidence suggests that planets can indeed survive. Some studies indicate that Earth-sized planets could even form after the white dwarf's creation from the debris disk left behind. The discovery of transiting planets around white dwarfs, where a planet passes in front of the star and causes a dip in its light, would offer a truly unique opportunity to study the atmospheres of alien worlds that have survived such a dramatic stellar transformation. These observations could provide crucial data on planetary composition and atmospheric conditions under extreme radiation environments, giving us clues about the potential for life in such long-lived, albeit peculiar, systems. The ongoing pollution of white dwarf atmospheres by heavier elements is also a vibrant field. Each new discovery of a metal-polluted white dwarf adds another piece to the cosmic puzzle, detailing the composition of rocky and icy bodies that once orbited these stars. This forensic astronomy helps us understand the diversity of planetary building blocks across the galaxy, shedding light on how common elements crucial for life, like carbon and oxygen, are incorporated into planetary systems. Beyond individual stars, white dwarfs play a subtle yet significant role in the larger cosmic tapestry. As old stars die and become white dwarfs, they lock up a significant amount of stellar mass, effectively removing it from the cycle of star formation. This contributes to the gradual chemical enrichment of the interstellar medium, as the planetary nebulae they shed return processed elements back into the galactic gas, providing the raw materials for future generations of stars and planets. They are silent, long-term contributors to the cosmic web, that vast, interconnected structure of galaxies and dark matter that defines the universe on the largest scales. In essence, white dwarfs are cosmic chameleons. They've transformed from fiery giants into dense, compact objects, yet their roles in the universe are incredibly diverse and impactful. They continue to be a fertile ground for discovery, pushing our understanding of extreme physics, stellar evolution, and even the ultimate fate of planetary systems. Their quiet, enduring presence reminds us that even in astronomical death, there's a universe of profound activity waiting to be explored. As research into white dwarfs progresses, we're not just confirming existing theories, we're also stumbling upon new phenomena that challenge our current models. One intriguing area involves the study of ultramassive white dwarfs, those pushing the very upper limits of the Chandrasekhar limit. These rare objects are thought to be the result of the merger of two less massive white dwarfs, a cosmic collision that can lead to an object so dense and massive it barely avoids becoming a neutron star. Such mergers could also be a source of type Ia supernovae, offering an alternative pathway to these powerful explosions that doesn't require a companion star. Another captivating aspect is the phenomenon of oscillating white dwarfs, also known as variable white dwarfs. These stars exhibit subtle, rhythmic pulsations in their brightness, much like seismic waves traveling through Earth. By studying these tiny variations, astronomers can perform asteroseismology, a technique analogous to seismology on Earth. By analyzing the patterns of these oscillations, scientists can probe the internal structure of white dwarfs, revealing details about their composition, temperature gradients, and even their rotation rates, much like how geologists use seismic waves to understand Earth's interior. This allows for a unique, otherwise inaccessible, look into the heart of these incredibly dense objects. These pulsating white dwarfs are vital for refining our theoretical models of stellar evolution and the physics of degenerate matter. They act as natural tuning forks, providing precise data that helps us test our understanding of fundamental physical laws under conditions far beyond anything we can replicate in a laboratory. In a more speculative, yet fascinating, twist, white dwarfs might even play a role in the ongoing hunt for dark matter. Some theories propose that certain types of dark matter particles could accumulate in the cores of white dwarfs, subtly affecting their cooling rates or internal structure. While still highly theoretical, precise observations of white dwarf populations could potentially offer constraints on these dark matter models, making these stellar remnants unlikely, but valuable, partners in one of the biggest mysteries in modern physics. The sheer adaptability and informational richness of white dwarfs continue to amaze. From their role in understanding cosmic distances and the universe's expansion, to serving as forensic tools for lost planetary systems and offering insights into the most extreme states of matter, these stellar corpses are anything but inactive. They are dynamic, evolving laboratories that continue to reveal the universe's profound complexity, proving that even in stellar death, there is an enduring and captivating story to tell. Yet, even as we unlock these secrets, white dwarfs continue to hold profound implications for the ultimate fate of the universe. Their incredibly long cooling times mean that they will persist for eons, far outliving even the longest-lived red dwarf stars. This makes them central to theoretical discussions about the heat death of the universe, a scenario where the cosmos eventually reaches a state of maximum entropy, with all energy uniformly distributed and no further thermodynamic processes possible. In this unimaginably distant future, a universe dominated by cold, dark black dwarfs, neutron stars, and black holes would be the final, silent act. The cosmic ballet of white dwarfs extends beyond individual stars. When two white dwarfs orbit each other in a binary system, their gravitational interaction causes them to slowly spiral inward, radiating energy in the form of gravitational waves. While these ripples in spacetime are incredibly faint, current and future observatories like LIGO and the proposed LISA, Laser Interferometer Space Antenna, are designed to detect them. The detection of gravitational waves from merging white dwarf binaries would not only offer powerful confirmation of Einstein's general relativity in extreme gravitational environments but also provide a new way to measure cosmic distances and potentially even understand the origins of some type Ia supernovae. The final moments of these mergers are thought to be violent, potentially leading to the formation of an even more massive white dwarf, a neutron star, or the aforementioned supernova. Furthermore, white dwarfs are increasingly being studied as potential cosmic lighthouses for probing the interstellar medium. The light from a white dwarf, passing through the vast expanses between stars, can be absorbed by various atoms and molecules in the gas and dust. By analyzing these absorption lines, astronomers can map the distribution and composition of the interstellar medium, providing crucial insights into the raw materials from which new stars and planets are formed. In essence, the ongoing research into white dwarfs is a testament to the fact that even seemingly dead objects in the cosmos harbor vibrant, active processes that continue to shape the universe and challenge our understanding of its fundamental laws. They are not merely endpoints but dynamic participants in the grand cosmic narrative, continually offering new puzzles to solve and deeper insights into the astonishing workings of the universe. And as our observational capabilities continue to advance, the humble white dwarf promises to remain at the forefront of astronomical discovery. The precision offered by space-based telescopes and the immense collecting power of next-generation ground observatories will allow us to scrutinize these stellar remnants with unprecedented detail. One of the most exciting prospects is the use of white dwarfs to pinpoint the ages of the very oldest star populations in the universe. Because their cooling is so predictable, studying the coolest, faintest white dwarfs can provide a direct measure of the age of the galactic disk, and even potentially the globular clusters, which are some of the universe's most ancient structures. This acts as a cosmic stopwatch, allowing astronomers to rewind the clock and understand the conditions of the early universe and the first epochs of galaxy formation. It's like finding fossil records that tell us exactly when the first life emerged on Earth, but on a cosmic scale. Beyond the scientific breakthroughs, white dwarfs continue to capture the popular imagination. Their extreme density and ultimate fate evoke a sense of awe and wonder. They often feature in science fiction as remnants of ancient civilizations, or as sources of immense power, even though their real-life energy output is modest compared to active stars. This blend of scientific intrigue and speculative possibility ensures that the stellar corpse remains a compelling object of study, both for seasoned researchers and for anyone gazing up at the night sky, pondering the ultimate destiny of stars. From their origins as the fiery hearts of stars, through their dramatic red giant phase, to their ultimate transformation into dense, cooling embers, white dwarfs are a testament to the diverse and complex life cycle of stars. They are not merely cosmic leftovers but active, informative participants in the ongoing story of the universe, continuously revealing new layers of understanding about physics, galactic evolution, and the very fabric of spacetime. Their quiet presence reminds us that even in astronomical death, there's an enduring and captivating narrative waiting to be explored. Beyond their individual mysteries, white dwarfs are increasingly becoming focal points in our understanding of the galactic ecosystem. The material they gently shed during the planetary nebula phase, rich in heavier elements forged in the star's core, returns to the interstellar medium. This enriches the gas and dust clouds, providing the building blocks for subsequent generations of stars, planets, and potentially, life. In a sense, every time a new star like our Sun forms, it carries within it the recycled remnants of countless stars that came before, including the material expelled by dying red giants that went on to become white dwarfs. This cyclical nature highlights the interconnectedness of all cosmic phenomena. Perhaps one of the most unexpected and exciting avenues of research is the connection between white dwarfs and the search for extraterrestrial life. While a white dwarf itself is a dying ember, its long, stable cooling phase could offer an extended period of habitability for any planets that survived the star's tumultuous red giant phase. If a planet is orbiting at the right distance, a habitable zone that shifts inward as the star cools, it could potentially maintain liquid water on its surface for billions of years, much longer than Earth will remain habitable around our Sun. This opens up the intriguing possibility of second-generation life around stellar remnants, offering a vast, unexplored territory in astrobiology. The discovery of polluted white dwarfs, hinting at devoured exoplanets, further fuels this speculation, providing tangible evidence that planetary systems can indeed persist around these stellar corpses. The study of white dwarfs is, in many ways, an art of stellar forensics. Each one is a crime scene, not of violence, but of immense cosmic change, preserving clues about a star's entire life and its dramatic demise. By meticulously analyzing their light, astronomers piece together the sequence of events: the original mass of the star, how long it lived on the main sequence, the elements it forged, and the chaotic events that led to its final, compact state. This forensic approach extends to their potential planetary systems, where the pollution acts as a chemical fingerprint of destroyed worlds, telling us what they were made of and how they met their end. In conclusion, the seemingly quiet existence of white dwarfs belies their profound significance in the universe. They are not merely the end of a star's life but a vibrant new chapter in cosmic evolution. From providing fundamental insights into extreme physics and spacetime, to acting as cosmic clocks in distant lighthouses, and even offering tantalizing clues about life in the far future, white dwarfs continue to be a source of endless fascination and scientific discovery, pushing the boundaries of our knowledge with every new observation. As our understanding of white dwarfs deepens, the focus shifts from simply cataloging these objects to unraveling their intricate roles in the grand cosmic narrative. We're moving beyond what they are to explore what they do and what they tell us about the universe's past, present, and far future. Even as they fade, white dwarfs continue to exert a powerful, though often unseen, influence. Their immense density creates a significant gravitational field that can subtly bend the light from more distant background stars and galaxies, a phenomenon known as gravitational lensing. While not as dramatic as the lensing caused by galaxy clusters or black holes, detecting these tiny distortions can offer a unique way to identify isolated white dwarfs that might otherwise be too faint to see directly. It's like finding invisible cosmic spectacles that subtly warp the view of the universe behind them, allowing us to weigh these elusive objects and refine our models of their mass distribution in the galaxy. Beyond their role in novae and type Ia supernovae, white dwarfs also bear witness to other cosmic cataclysms. The debris disks observed around some of them aren't just remnants of devoured planets. They can also be formed from the tidal disruption of asteroids or even small stars that strayed too close to the white dwarf's intense gravitational pull. Studying the composition of these disks, and the way they feed material onto the white dwarf's surface, offers a real-time glimpse into the destructive power of gravity in extreme environments. It's a cosmic demolition derby playing out in slow motion over millennia. In essence, white dwarfs are becoming the ultimate cosmic archaeologists. Each one is a dense archive of information, storing the history of a star from its birth to its quiet, drawn-out demise. By carefully analyzing their light, their pulsations, their magnetic fields, and the debris they accumulate, scientists can reconstruct the life story of billions of stars across the galaxy. This forensic approach allows us to not only understand individual stellar destinies but also to piece together the broader evolutionary history of star clusters, galaxies, and perhaps even the universe itself. From the most energetic supernovae to the quiet cooling over eons, white dwarfs are far more than just stellar remnants. They are dynamic participants in the ongoing cosmic drama, constantly revealing new layers of understanding about the universe's profound complexity and its astonishing, never-ending story. Beyond their individual mysteries, white dwarfs are increasingly becoming focal points in our understanding of the galactic ecosystem. The material they gently shed during the planetary nebula phase, rich in heavier elements forged in the star's core, returns to the interstellar medium. This enriches the gas and dust clouds, providing the building blocks for subsequent generations of stars, planets, and potentially, life. In a sense, every time a new star like our Sun forms, it carries within it the recycled remnants of countless stars that came before, including the material expelled by dying red giants that went on to become white dwarfs. This cyclical nature highlights the interconnectedness of all cosmic phenomena. Perhaps one of the most unexpected and exciting avenues of research is the connection between white dwarfs and the search for extraterrestrial life. While a white dwarf itself is a dying ember, its long, stable cooling phase could offer an extended period of habitability for any planets that survived the star's tumultuous red giant phase. If a planet is orbiting at the right distance, a habitable zone that shifts inward as the star cools, it could potentially maintain liquid water on its surface for billions of years, much longer than Earth will remain habitable around our Sun. This opens up the intriguing possibility of second-generation life around stellar remnants, offering a vast, unexplored territory in astrobiology. The discovery of polluted white dwarfs, hinting at devoured exoplanets, further fuels this speculation, providing tangible evidence that planetary systems can indeed persist around these stellar corpses. The study of white dwarfs is, in many ways, an art of stellar forensics. Each one is a crime scene, not of violence, but of immense cosmic change, preserving clues about a star's entire life and its dramatic demise. By meticulously analyzing their light, astronomers piece together the sequence of events, the original mass of the star, how long it lived on the main sequence, the elements it forged, and the chaotic events that led to its final, compact state. This forensic approach extends to their potential planetary systems, where the pollution acts as a chemical fingerprint of destroyed worlds, telling us what they were made of and how they met their end. In conclusion, the seemingly quiet existence of white dwarfs belies their profound significance in the universe. They are not merely the end of a star's life but a vibrant new chapter in cosmic evolution. From providing fundamental insights into extreme physics and spacetime, to acting as cosmic clocks in distant lighthouses, and even offering tantalizing clues about life in the far future, white dwarfs continue to be a source of endless fascination and scientific discovery, pushing the boundaries of our knowledge with every new observation. One of the most enduring mysteries centers on magnetic white dwarfs. Roughly 10 to 20% of all observed white dwarfs possess incredibly strong magnetic fields, some billions of times more powerful than Earth's. The origin of these extreme fields remains a puzzle. Did the white dwarf inherit the magnetic field from its progenitor star, perhaps amplified during the star's collapse? Or are these fields generated anew during the white dwarf phase, perhaps through some form of internal dynamo or a merger event? Unraveling this enigma is crucial not only for understanding white dwarfs themselves but also for gaining insights into stellar magnetism across the entire spectrum of star types. Beyond the visible and known, white dwarfs might even be silent sentinels hinting at the presence of the universe's most elusive components. Scientists are exploring whether some white dwarfs could have unseen companions, not just other stars or planets, but potentially even exotic forms of dark matter. While speculative, precise measurements of white dwarf motions, cooling rates, or subtle gravitational effects could, in theory, reveal the gravitational tug of dark matter clumps or even primordial black holes orbiting them. Such discoveries would be revolutionary, turning these stellar remnants into unexpected probes for the invisible universe. Looking even further into the cosmic timeline, white dwarfs provide the most concrete observable link to the deep future of the universe. As the cosmos expands and cools, and as hydrogen fuel eventually runs out, star formation will cease. The remaining red dwarfs will slowly burn out over trillions of years. The ultimate outcome will be a universe dominated by these stellar corpses, black holes, neutron stars, and the theoretical black dwarfs. These final, cold remnants will be the only enduring monuments to stars that once blazed brightly. Their study isn't just about what they are now, but what the universe will become in the unimaginably distant future, a silent, dark cosmos where the last whispers of stellar light have finally faded. In every facet, from their extreme physics to their role in cosmic evolution and their potential as probes for dark matter, white dwarfs continue to be a source of awe and scientific inquiry. They are a powerful reminder that even in stellar death, the universe offers endless frontiers for discovery, constantly challenging our perceptions and expanding our understanding of the cosmos. And the journey of discovery surrounding white dwarfs is far from over. As our technological capabilities continue to grow, we are pushing the boundaries of what's observable, revealing ever more subtle and profound aspects of these fascinating stellar remnants. One of the most exciting advancements lies in our ability to perform incredibly precise measurements. Techniques like astrometry, which involves meticulously tracking the tiny shifts in a white dwarf's position against the background stars, allow us to detect the gravitational tug of unseen companions, even very low-mass planets or brown dwarfs that are too faint to observe directly. This weighing of the invisible provides crucial data on the prevalence of substellar objects orbiting white dwarfs, hinting at how common planetary systems are around such evolved stars. It's a testament to the power of precision astronomy to reveal what's otherwise hidden. White dwarfs also play a vital, often understated, role as cosmic recycling plants. The material they shed during the planetary nebula phase, enriched with heavier elements like carbon and oxygen forged in the star's core, disperses into the interstellar medium. This enriched gas and dust become the raw ingredients for the next generation of stars, planets, and even the building blocks of life. Every atom of carbon in your body, for instance, was likely fused in the heart of a star that eventually became a white dwarf or a more massive star that exploded as a supernova. This continuous cycle of death and rebirth underscores the profound interconnectedness of all cosmic phenomena. While highly speculative, some theoretical physicists even ponder whether white dwarfs, with their extreme densities and unique quantum properties, could offer indirect clues to exotic physics beyond our current understanding, perhaps even hinting at dimensions or particles that interact with matter in ways we're only beginning to imagine. While this remains firmly in the realm of theory, it showcases how the study of these seemingly dead stars can inspire profound questions about the very nature of reality. In essence, white dwarfs continue to be a fertile ground for discovery, pushing the limits of our understanding across astrophysics, quantum mechanics, and even cosmology. They are silent, enduring testaments to the dynamic and ever-evolving nature of the universe, each one a compressed cosmic library waiting to reveal its next secret. In the grand cosmic ballet, where stars are born in dazzling nebulae and live out their lives fusing elements, the white dwarf stands as a profound testament to stellar evolution. Far from being mere cosmic ashes, these dense, Earth-sized remnants are vibrant laboratories of physics, active participants in galactic processes, and silent chroniclers of the universe's history. From their incredibly compact nature, sustained by the enigmatic electron degeneracy pressure, to their role as standard candles for measuring cosmic distances and their dramatic involvement in novae and type Ia supernovae, white dwarfs continually push the boundaries of our understanding. They serve as cosmic clocks, allowing us to accurately date the oldest star populations. Their polluted atmospheres offer a unique archaeological record of devoured exoplanetary systems, hinting at the diverse fates of worlds beyond our own. Even in their gentle cooling over eons, they raise profound questions about the ultimate heat death of the universe and the hypothetical black dwarfs that await in the unimaginably distant future. The ongoing study of magnetic white dwarfs, their subtle oscillations revealing internal structures, and the potential for their light to probe the interstellar medium ensures that these stellar corpses remain at the forefront of astronomical discovery. They are not static monuments to a bygone era but dynamic players in the ever-evolving cosmic narrative, constantly revealing new secrets about matter under extreme conditions, the life cycles of stars, and the grand, interconnected tapestry of the cosmos. Ultimately, the white dwarf reminds us that even in astronomical death, there is an enduring legacy, a wellspring of scientific inquiry, and a deep, captivating story waiting